Alright then, so my name is Colton Stranger-Thorsen. This is my Capstone project on one-stroke engine. So now I'm guessing a lot of you don't know much about engines, so let's just quickly go over them. So there's two main types of engines for gasoline at least. You have 4 strokes and you have 2 strokes. So what a stroke is a stroke is defined by every time a piston moves in one direction. So for a 4-stroke essentially, which is in all of your cars, it will suck in fuel and air, it will compress it, it will explode and come down to the power stroke, and then it will expel the exhaust. So as a 2-stroke, it just does it for 2. So it compresses, it explodes, right? But then it sucks in fuel and air and power strokes, and compresses and sucks out the exhaust. So it's just, for every cycle, there's only 2 strokes to it. So what is happening is, just because I know not a lot of you know much about engines, just let's quickly go over a couple of the basic parts. Okay? Piston. This thing right here, this is what generates a spark to start the explosion, therefore we call it a spark plug. I love engineering terms. This rod right here connects the piston to the crankshaft, connecting arm. Okay? Anyway, so the thing that spins is called the crankshaft. That's what delivers the power from the motor to the transmission, essentially, from there. So the piston's actually what does most of the pressing, etc. I think you can get it from here. Alright, so then let's just go over some more engines that they're not necessarily stroke-based, because we have rotary engines are just not considered stroke-based because they kind of defy what we think of as a stroke. And if you try to define this, then you quickly run a problem with something like a Soviet 5-chamber rotary engine. What the crap is this? Anyway, so we also have like electric engines, and just because of how they're made, we don't define them as strokes. So, just clearing that up. Now there is one company that claims that they have a 1-stroke in engine. Now the thing is though that it's not a 1-stroke. Everybody agrees it's not a 1-stroke. Nobody really knows what it is though. In essence though, it uses 2-stroke philosophies for 2 pistons that do 2 motions before the cycle repeats. Therefore, it can be classified as a 2-stroke. It is pretty cool though because it's 500 cc's of displacement, which is really small for an engine. A lot of motorcycles have engines that big. And then 120 horsepower is actually quite a lot. So my Jeep makes 190. So then, who am I? Well, I'm a wrestler, I used to race motorcycles, I'm a certified SolidWorks professional, and I'm a hiker, backpacker, scouter, and yes, I will be Eagle. My Eagle Scout project will be fully installed by this Wednesday. And then for college of choice, I'm going to be going to Embry-Riddle Aeronautical University in Prescott, Arizona. Don't worry, most people haven't heard of that. And so who's going to be assisting me with this? Because clearly, I know nothing about engines. So I need a team that's going to help with this. So we have Jack Close because he has a CSWE. Whenever I need something from SolidWorks that I can't get out of it, I ask him, he tells me what to do, and it works 99% of the time. So then we have Ian Williams, because I have 3 other classes with him. And so naturally, it's great to bounce ideas off of him at any time. If you've ever taken any engineering class, you know that sometimes you get ideas at the most random spots, so he's just great to bounce ideas off whenever. And I have Kevin Schmitz, he's my future advisor. He gives me solutions to problems that aren't yet there. For example, I asked him, how do you like my chamber? And he said, your chamber's really long, so your connecting arm is going to snap. I didn't care. I'm like, great, how's my chamber? Meanwhile, the next day, at the end of class, I put in my connecting arm, and I'm like, okay, well, Kevin was right, it turns out, like always. And then nothing was said to him. So he's my simulation saver. We'll get back to that in a minute. And then Kyer is my honest monotone opinionator, because sometimes you just need someone to look you in the face and tell you exactly what you need. And then Jay Stranger-Thorsen. He's my enthusiast and outside mechanical advisor, and he's also my dad, so he can see the broad overview and not what happens every single day. All right, so then I do have 2 expert advisors. I have Marco and I have James Colton. So he works with a company that builds 2-strokes, and this was great since my 1-stroke engine was going to use a bunch of 2-stroke philosophy. The only problem is he lives in Germany. So there's not only a communication barrier with language, but also with time zones. So it made it very, very difficult to communicate with him and very lengthy as well. So I ended up enlisting James Compton, who I have multiple avenues of connection with, as well as he knows plenty about motorcycles because he builds custom motorcycles for a living. And with this, he helped me so much, just making sure my model can be the best that it can possibly be. The only problem is I only got him halfway through the year, so I had to catch him up on a lot of stuff, which made the first hour talking to him kind of rough. because I need to catch up on a lot of progress. So then, what are my goals? Well, I want to have the project completed without any major timeline changes. And if you know anything about any of your Capstone presentations, this can be this. And I also want to have a good physical model. I want to have a 3D model that I can just spin around as a desktop playtoy. I want a non-lopsided model, where I didn't want there to be a lot of detail over here and then none over here. I just wanted to be more or less symmetrical with how much detail it has. I wanted to learn how to do good simulations, and I wanted to make it realistically able to be built in mass. Because that feels like something an engine should be capable of, right? Okay, thank you. So then what does this mean for success? I want a CAD model of an engine that can be classified as a one-stroke, while being able to be run for a short time if it is pursued further. Just a viable model, essentially. So for this, we had to have a company. So here's a QR code if you want to go to it. I doubt that any of you do. But my company is called Quadrant Dynamics. And I am terrible at art. If you know anything about me, you know that. And so this is what I did in an hour and a half of my time. That looks like garbage. I mean, if this is a business card and you got handed it, what is the first thing you would do with it? Donated it to the garbage, right? So I then asked ChatGPT for something, and it's been meaning out quite a lot. And this was a piece of it. I then edited it to actually include my whole title and everything. And I really like this design because it's complicated in a seemingly useful fashion. And if you know anything about my engineering, very on brand. So backing up for a minute, I didn't know a single thing about engines, especially on a building. So I decided to build a four-stroke model, something that is akin to something that actually exists. This is a four-cylinder, four-stroke model, and is very similar to those in some Jeeps. And I did this through all the first semester, and it went extremely productively. And you'll see why in quite a minute, but I'm fairly happy with this. You see that the valves are going up and down, and it actually looks kind of like an engine. Right. So some initial final designs. This is where Kevin was extremely helpful, more so than even one of my expert advisors. So he took a piston looking like this and a connecting rubber looked like this and turned it into these. Because I got really lucky. He had to download solvers on his computer for his project to work at all. And what that meant is that he could look over my shoulder while his computer was just doing computer things and tell me exactly what I needed to do. And this set the groundwork for how in-depth I wanted my model, non-lopsided, so I could confidently state that this is what an engine looks like, not this. This looks like a valve. It might be a valve. So then I took that knowledge and took that level of depth and added that to the crankshaft, which turned out great as is. And then I took a picture of a spark plug and I built one in reference to it. And honestly, that came out really well. And then, of course, we had the back. This simulation is 5 FPS. So whenever you say your game is running at 1 FPS and it looks like this, it's not. It's 5 FPS. Come on. So then there's just one problem with the engine I showed you earlier. This is called a camshaft. It's what makes the valves go up and down on a basic level. You can see that it's right here. Right? The problem is you need an intake valve and an extake valve, which means on this model, or per chamber. So on this model, I would need two camshafts. And that's not how engines are built. That's not how engines work. And also it took 18 minutes to simulate it. That was fun. So then I also had to look. I don't know why it did this. I don't know what setting changed. My own computer doesn't do this. My computer for engineering tech doesn't do this. Only this computer. Look, I don't know. Software doing software things. So then we get to the end product. You can see that I did consolidate the camshaft into one. I didn't have to have two. And this actually took quite a while to do. It took like an hour just to rotate the chambers, just because of how I built them in the first place. But overall, this actually came out pretty good. And in case any of you want to build your own engine, I don't know why, but if you want to simulate something like this, don't simulate the pistons. Simulate the crankshaft. Yep. The crankshaft will spin. It makes your life significantly easier. Just like that. Don't worry, this is the longest simulation I have. And that's it. So, timeline first semester. So, by the fourth to last week, I was 3 weeks ahead of schedule. I ended on time. What do you think that means for how long I spent simulating this stuff? I just planned a week of simulations, and it ended up being 4. And because I got all of this done, I built my model very, very quickly, and then just simulated for the rest of the time. I got stuck doing simulations for a while. It's perfectly fine. So the mid-year review, honestly, the package turned out way better than I thought it was going to turn out. And everything was going extremely well. I got ahead of schedule at some points, and there's just 2 things that went wrong. I put valves in a 2-stroke, because that engine was supposed to be a 2-stroke. 2-strokes don't have valves. That's not how they work. They have openings and very, very complicated mechanical contraptions called expansion chambers, which essentially creates a vacuum while in 0 moving parts. So these openings don't have valves. Not a good idea. You can see, no valves, openings. And then I could not figure out how to do a flow simulation. This is also when Kevin really helped out because his project was pivotal on flow sims. So naturally, I was like, okay, I'm going to do a flow sim, and Kevin's going to teach me how to do it. 3 weeks later, and Kevin got his first flow sim, I decided that was not going to happen. So how could a 1-stroke engine be made? Because this is my capstone project. All the others was just me learning how to do an engine. So how could a 1-stroke be made? Well, I had 2 kind of scratch designs that I put down on the whiteboards in the cabinet. So one of them, they both kind of presume the same philosophy of using both sides of the piston in order to create 2 chambers with the same piston. This means that if I use 2-stroke philosophies on both of the chambers, then it will explode every single time the piston moves, thus creating a 1-stroke. The only idea, though, was do I use this using a sleeve design around a big crankshaft, or do I do more of a normal kind of crankshaft design with connecting arm and then add a contraption to it? I went with the sleeve design since I just thought it looked better. Little did I know. So, first attempt, this thing was snapped instantly. All of you can tell me that. I don't care. So, what ended up happening is that I learned that if I have a displacement that I want the piston to get per chamber, and I know my compression rate, I can then function for the radius of the piston and how far the piston will travel. So with that, if the piston travels as far as the diameter of the crankshaft, and the connecting arm needs to be twice the length of the crankshaft, I can build a model, I can build a function that tells me the length of the connecting arm as it relates to the radius of the piston. Using that, I can build a model that doesn't absolutely suck. And so I had some explosions along the way because SolidWorks doing SolidWorks things. And you know SolidWorks, you know this is quite common. So right there you can see part of my crankshaft with these 2 outer parts, or the 4 outer parts that were coming in the other parts. These giant bricks here, or it should play again. These bricks here, that's essentially my engine block with the chambers, the spark plugs, and the pistons. The reason they separate is because I was too lazy to actually put them into one model because I had an earlier project, right? My preliminary engine, I just copy and pasted the spark plugs. Or sorry, not yes, the spark plug, but also the pistons. So, and just to be sure, these rods right here just contain the pressure since I have something sticking out of the chamber. And then moving on, why did this take so long? Because I did a bunch of simulations. And in almost every single one of these simulations, at least one thing is different. Because I would simulate, realize I did something wrong, fix it, resimulate. And I was getting about 2 or 3 simulations per class period. So it was not super productive, but I at least was working every single time. And continue some more because this, I didn't understand it. I couldn't understand it, and I still don't understand it. I don't know why this works. It did. I don't know why. Because you have velocity in the y, but it's linear, so it's like constant acceleration, kind of. Shouldn't that mean that, anyway, I couldn't figure it out. But this was first semester, and it would take like 15 or 20 minutes just to get to this. And then I realized that second semester I could just do this. 0, 5, number of times I want to rotate times 360, and okay, and it would do everything for me. It took 30 seconds. It was so much more efficient. And with this, it made it so that I could change something really quickly. Here's this model, for instance. Now, this was springs, and I thought springs were cool because I was in physics C, and I could do a bunch of different stuff with springs. Yeah, no, this sucks. My expert advisor looked at me and said I'm an idiot, and I should just force it, so I did. And this would be much more effective. And so I could resimulate everything. So that didn't take 5 hours of my life. And if you know anything about SolidWorks, this is what you know. And this is cadency at 196, and this is cadency at 196. This was really fun to wake up to one morning. Jeez. It's all we're still in SolidWorks things. So now, because of those errors, I rebuilt my model a couple different times because it's not worth my time to get rid of all those errors. I tried for 30 minutes, got through a third of them. And so with this, the crankshaft's rotating all at once, and that's how you get a barrel rolling cock. That was fun. So this is finally alternating in sync, but I still needed to update my connecting arm design, so I couldn't quite necessarily keep it. I ended up with this model. The reason this model isn't extruded back is because, remember that explosion from earlier? Right. Can't copy and paste that. And so timeline second semester, honestly I was more or less on time for the remainder of the year because I would fix something, simulate, fix something, simulate, fix something, simulate. It's because that, honestly, it went pretty good, except for one part. Right here. I have it saying print one stroke, print two stroke. The problem is, that's a machine doing it, not me doing it. So naturally, I didn't have any time to do this. Like, I had free time essentially. I unknowingly built in 4 weeks of free time. That was not good. And there's a giant problem. I didn't actually start printing because I thought I was going to keep reiterating on my designs. So that really delayed my printing process until almost everybody in this class was using the printer. So I couldn't actually get a good 3D model. You'll see that here. So my end model, it's 8 chambers, 4 pistons, 1.5 liters of displacement. It is one in standard designs, and I'll show you just how much in just a second. But it is tiny. So I took this full version of this, so duplicated back 4 different times for a total of 6 liters of displacement, and compared to a Cummins 6-liter engine. And it is almost half the width, less than half the height, and less than half the length, while being the same displacement and less than half the weight. Essentially, it is a much smaller, much lighter, while still being the same power outage. Or, guess that, actually. Likely to work though with Cummins? 100%, but it should be 100%. They've been around for 106 years. I give my model about a 20% chance of being viable if we pursue it further, mainly because what ends up happening is this engine concept has been around for less than 106 weeks. So it's actually not going to work right now. Sorry about me. So now some calculations. I did a rough ballpark because each chamber of mine is 187.5 cc's to get one ring to be 1.5 liters. So then with that, I took 125 cc two-stroke, which makes about 30 horsepower. And I then calculated my engine using 30 horsepower per chamber just to try to get a little bit of a tolerance in there because I am not actually good at designing engines. I learned this. And if we do that, my engine makes 960 horsepower. A naturally aspirated 6-liter, so a normal one if you will, would make between 350 and 400 horsepower. So mine could, in theory, make 2 to 3 times the amount of power as a normal 6-liter engine. My Jeep, for reference, makes 190 horsepower. I know it's not the fastest thing in the world, but 960 horsepower is nothing to joke around with. So did I succeed? Yes. I met 4 of my 5 project objectives. I did not have any major timeline changes. I mean, I'm not going to count getting ahead as a change. And I have a non-lopsided model. I had learned how to do good simulations, and I made it realistically able to be built in max, or at least I believe so, because it has no extremely awkward geometric parts, and it has realistic tolerances for what I'm trying to do here. I do not have a good physical model. Like I said, I should have been smart about that. Learning experience. Okay. So what would I do with more time? I would find the stoichiometric ratios that I would need. In essence, that means how much gas do I need to put in for biggest bang? And find the optimal flow sizes, or inlet sizes. So because 2-strokes, they have holes, not valves. So naturally, where should I actually place them? How big should they be? And I also need to implement a cooling system, an oil system. Max RPM calculation would be nice. Minimum crankshaft size, because a crankshaft is used to propel the piston back up. But my piston explodes every single time, so I don't need that. So that's where a lot of the weight savings happen. So how can I minimize that crankshaft? So then also stress tests would be kind of nice, just try to understand where it would fail, as well as power band calculations, because 2-strokes, they don't make more power across the board. They make more power at a little 1,000 RPM range, or 2,000 or 3,000, depending on your exact specifications, versus a 4-stroke. That's why you don't see them in your cars. And then also exhaust system, because expansion chambers would take a year in and of themselves, and I might want to patent it, I don't know. So then, what do I hope the future holds for it? Well, honestly, currently, in its current state, it cannot be built. Or at least, it wouldn't work very well. So I'm kind of hoping that some person finds this on YouTube or something, and on their own one-stroke journey, and tries to improve the design, in which case it's in the file folder. Or I should patent it, I don't know. And then what I recommend Capstone, well, it depends on who you are. Because the journals, they are super realistic, but they're super time-consuming, and I don't think a single person in our Capstone class put that into their timeline. So just be wary of that. They are super realistic though. Companies and career comparisons, if you're the kind of person that thinks you're going to come into the class and immediately start working on something, it's not. You have a quite a long lead time on it. And then it also depends on the project. It needs to be research-based almost to the last day, and at least I think I found the heavy emphasis that gets me ahead of schedule. Because the last journal we did was journal 5, and we had 3 weeks to do it. But I was 4 weeks ahead of schedule. So that really messed me up. And any questions?
Questions?
Yeah.
What would the advantages be over other engines, and how does it compare specifically to electric engines, as the car industry is generally shifting towards that?
I don't understand. I do not research electric engines enough to understand the comparison between this engine and an electric engine. Although compared to gas engines, this engine is significantly smaller and significantly lighter, while delivering significantly more power for a significantly shorter amount of time. Yes, Jarrell?
That 960 horsepower metric for something that's like half the size of a V8 is incredibly, I want to say, terrifying. How did you get this number?
So how I got the number is, I'll go back to that slide that you're talking about. Right here. So what I ended up doing is each chamber on my engine is 187.5 cc's. And a 2-stroke dirt bike, one of the models is a 125 cc bike. So what I did is I took the power output from this 125 cc bike and I said, and estimated essentially, that that's the amount of power that each chamber of mine can produce, since I knew there's going to be quite a lot of loss with my design. And so then when you multiply that through my entire engine, that's how you wind up with the 960 horsepower. Yes?
Sorry, one more thing. So because it's one stroke and you're going with cylinders that are rotating like this, have you considered the effects of like knocking on your engine and it just potentially not even working after like, let's just say 40 cycles? Have you done anything to combat that?
So just, sorry, can you repeat that?
Have you done anything, have you accounted for knocking within your engine where slight misalignments could cascade into large, massive system failures?
In its current design, knocking is the least of my problems because there are many things that would destroy the engine much faster than that. Will that be a problem? Yes. Is that a problem for me right now? No. Yes, that's all?
So, even without considering your own one-stroke, do you believe that just one-strokes in general do have a future here, or is it just limited to 4-strokes?
Oh, I don't know, but I thought of the designs that could kind of help, but I was curious if it would work or not. And my only other capstone idea was a shoe, so I went with this. I'm not joking, it was literally... No. No idea. Because essentially I tried to do a torque calculation on what I thought was going to be the highest likelihood for a failure, and I got like 60,000 in, so I don't think I did it right. Yes?
I might be repeating a question he just asked, but I didn't hear it. Did you do a torque calculation ever?
No. The only one I did just spit me on a number that clearly wasn't real, okay. So I think I messed up on my physics. Yes, Kevin?
Do you ever have a plan to actually cast a block for this, or will it just be basically the piston sticks?
No, I did not have a plan to cast this for a block.
Really?
Yes.
So if you were to keep pursuing this, do you think you'd like more focus on longevity, or would you use it like motorsport?
That's a great question. So I think my primary focus would need to be to build it, because I actually found a failure point that I didn't know about until I started 3D printing it, and I realized it was a huge flaw. And it would snap after like half a rotation, essentially.
Ooh.
So I would need to build it in order to find out what I would need to fix in order to make it have a higher longevity, essentially, is what you're saying. So I guess I would focus on longevity more so than power, since it makes a stupid amount of power as is. Any other questions? Discos?
Hey, CST, did you model yours after more like the Wankel, the rotary engine? It kind of, I mean, the motion is very similar to the,
I did not model mine after a rotary engine. What I did is that I just took my model and I'm like, oh, that looks like it could be mirrored. So I mirrored it. And I'm like, oh, that looks like it could be rotated. Hey, it could be rotated. Look at that.
okay, that works. All right. Any other questions? All right, good job.